Hello, everybody. Welcome to another episode of Science Like Me Plus. I am Shanjoy Das Gupta. I'm a professor here in the Computer Science Department at UC San Diego. And today I'm very pleased to have our guest, Ellen Vitercik. She is an assistant professor at Stanford University. She has a joint appointment in computer science and also in management science and engineering. Ellen got her Ph.D. in 2021, and she has won a whole bunch of awards at that time and since then. She got multiple awards for her dissertation. She won the Miller Fellowship at UC Berkeley. She won the AI 2050 Fellows Program, and she also has an NSF Career Award. So all of this is very impressive, and we are extremely lucky and pleased to have her with us today. So, Ellen, I was hoping that we could get a little bit of a sense of some of the things that you work on, and also your view of the field in general, because these are times of great change. So perhaps we could, perhaps a good place to start would be on something that seems to be a really central theme in algorithms these days, namely beyond worst case complexity.
Sure.
So it's like, what is that, and how does it relate to your stuff?
Yeah, sounds good. And yeah, thank you for the introduction. So I work on using machine learning to improve algorithm design and improve the time it takes us to solve really hard optimization problems, namely like NP-hard optimization problems. And so if we think about the way that we learn algorithms in undergrad, we learn algorithms in the framework of worst case analysis, where we're trying to understand, well, what problems are polynomial time solvable in the worst case and what problems are not poly-time solvable in the worst case, and what is the runtime of those algorithms in the worst case, and this kind of like worst case analysis framework. And I got interested in this area of beyond worst case analysis in my PhD because I was kind of curious about other ways of thinking about how we design algorithms, and just other ways of thinking about computability. And in large part, this was because if we think about a lot of the hard optimization problems that we actually encounter in practice, these often are NP-hard problems, but somehow that doesn't scare practitioners away from trying to solve them. And so there's just this gap between the way I was taught algorithms, especially as a more mathematical, theory-oriented student, and the way that people seem to think about algorithmic problem solving in practice. And I became really interested in this idea of beyond worst case analysis, and if there's other ways we can think about how hard a problem actually is to solve. And so the way that the kind of type of research I've done in this perspective is understanding if we're trying to solve a really hard problem day after day after day, kind of the shipping problems that a shipping company has to solve day after day, those routing problems, is there some structure shared across the problem instances that that are coming up in practice that could somehow allow us, if we can uncover the structure and leverage the structure, solve these problems faster?
I see. Yeah, I mean, so when I was in grad school, I think the very pessimistic view of algorithms was still in full force. And it really was a very damning picture. It really seemed like just about everything we want to solve is NP-complete, which means that either you can solve all of them or you can solve none of them. And somehow people seem to overwhelmingly believe that actually you can solve none of them. So it's nice that now, the news seems somewhat better, that actually these pessimistic results were only if you look at the very worst possible case, and that in practice, the picture is somewhat rosier. But I feel like we are still teaching the bad news to undergrads. Is that just a UCSD thing, or is that also a Stanford phenomenon?
No, yeah, I think, well, I think that this worst case framing is very important. And certainly the way that we're still teaching algorithms at Stanford as well is through this worst case framing. Um, but when I taught algorithms this past quarter, I did try to like hint at this beyond worst case framing for perhaps some more kind of like practically inclined students who do have this kind of question mark in their head as they're learning about worst case analysis. We also have at Stanford a class that was designed by Tim Roughgarden, who's one of the early people in this beyond worst case analysis space on beyond worst case analysis. So I taught that. That was more of a kind of like upper level undergrad and Ph.D. level class. But still, I think the curriculum there is still being developed. And I guess the interesting thing about this area is that there's like new research all the time that could be developed from a curriculum perspective. So it's a ever evolving area.
Yeah, I feel like we should be doing a lot more of that here. And thanks for thanks for saying that. It definitely inspires me to create a class of this kind. Yeah, one of the strange things about the theory of NP completeness is that you have this huge list of problems, like tens of thousands of problems, and they all sound really different. There's Boolean satisfiability, the traveling salesman problem, scheduling problems, and yet they all turn out to be equivalent to one another when it comes to the issue of polynomial time solvability. And that's kind of bizarre because they seem so different. So do you feel that now that we're thinking more about beyond worst case, that these problems regain some of their individuality, that we are now not just clumping them all together any longer?
Yeah, that's an interesting question. I think, at least from my perspective, the way that I come at beyond worst case analysis is really from a more like mathematical programming kind of like perspective. So I'm actually very passionate about the ways that these kind of like broad ways that we can represent NP-hard problems like integer programming or like satisfiability problems, and trying to develop the solvers that do solve these very broad and very very broadly encompassed kind of types of formulations. But at the same time, something that I'm really excited about in this particular space is these solvers for, say, like integer programming solvers or SAT solvers. They have been developed very generically. Like when you give a problem to, say, an integer programming solver like Gurobi, it should be able to solve the average integer program like pretty quickly. But I think like with the rise of like Gen AI and LLMs, there's a lot more scope. We've already seen a lot of examples of this to develop using machine learning a lot of amazing like very problem-specific heuristics. So if you're trying to solve your specific type of vehicle routing problem or your specific type of like medical resource allocation problem, I think there's becoming more and more ways to design algorithms and heuristics that are very well designed for the particular problems that you're trying to solve. And there could be scope to take like a broad framework like integer programming or like a Gurobi optimization solver and integrate these very problem-specific heuristics into this broader framework. So I think like LLMs have really opened up this space to both take advantage of like the broad frameworks like integer programming and Gurobi, but also take advantage of like the very problem-specific heuristics that you can possibly develop with the aid of machine learning.
I see. So there's something like integer programming that can apply to tons of different problems and is applied to tons of different problems, but in the worst case, takes a long time. And then there are heuristics for speeding it up. And these heuristics do not impact the correctness of the procedure. So it remains, it gives you the right answer at the end.
Yeah. So that itself that's a really important question to ask in this space. It is really important that when we use these tools like integer programming solvers or SAT solvers, that we are maintaining some guarantee of optimality. That's why we use them. But I guess a very interesting research problem is that then when I use machine learning or LLMs and try to improve these optimization solvers, what is the right way to be leveraging these tools in such a way that we don't risk losing that very important formal optimality guarantee.
I see. So it's so somehow ML is used to select heuristics for improving the performance of these solvers.
Yeah, exactly.
And so has that worked out pretty well so far?
I think it's definitely still an evolving space. So already, so for example, with like AlphaEvolve or these types of pipelines coming out of DeepMind, we've seen a lot of interesting kind of problem-specific heuristics developed that seem to have pretty impressive performance. But I think there's still a gap between these very problem-specific heuristics, which don't have any kind of like proof of optimality, and then these solvers where the proof of optimality is like of central importance, and kind of understanding the landscape between them is something I'm really interested in.
I see. Now, I know that you also have a lot of work on LLM reasoning because these language models seem to have some sort of reasoning ability, and they certainly seem to express opinions with confidence and then provide some sort of justification. But I know you've been trying to get to the bottom of of how sound this reasoning actually is, and if you could say a little bit about your work in that.
Yeah, so we've been interested in algorithmic reasoning and we and other labs have been interested in algorithmic reasoning as a way to understand LLM reasoning, because with algorithmic reasoning, well, oftentimes the question and the answer, so say the question is, here's a graph, what's the shortest path between A and B? Or here's an array, what would be a sorted version of the array? It's extremely verifiable, the final answer. We can programmatically understand what the final gold truth answer ought to be. But we don't know when we ask a model one of these questions, like how is it solving this problem? Does it look anything like how we as humans solve the problem, or is it doing something completely different? And what's cool about algorithmic reasoning is that we have a lot of well-developed kind of hypotheses of, if we were a human approaching, say, a shortest path reasoning problem, how would we approach it? We might approach it using Dijkstra's algorithm or using the Bellman-Ford algorithm. And so with these well-formed kind of and verifiable hypotheses, we can then test, like, okay, is the LLM doing something like Bellman-Ford? Is the LLM doing something like Dijkstra's? And so the specific angle that we've been looking at this problem at is, well, in ICML this summer, we have a paper on data structure reasoning. So looking at data structure tasks as a very well-structured and very easily verifiable way to test kind of like reasoning primitives, I would say, like linear reasoning, hierarchical reasoning, and things like that. So for example, we can ask things like, okay, here's an array. If you were to add this element to the array and maintain the state that the array must be sorted, what answer do you get? So very simple, like linear reasoning skills. Then you can start to probe like compositional reasoning ability. So if I add multiple elements to this array, if I delete some elements, what kind of state do we end up with? And also more complex kind of like hierarchical forms of reasoning, which can be represented via trees and graphs and things like that. And we can also, my kind of like favorite aspect of this work is also understanding kind of like very out of distribution reasoning abilities. So for example, if you ask an LLM like a data structures task on a very nice uniform kind of like problem instance, the LLM will also often get the correct answer, because that's kind of what the data structures task would look like in a textbook. But if you ask the LLM to do this data structures reasoning on a very non-uniform, very kind of like structured instance, oftentimes the reasoning will somehow break down. And our hypothesis is that kind of non-uniform instances are very different from the types of things that you see in textbooks. So it kind of displays this out of distribution, lack of generalization.
But then it sounds like it's really not learning the definition of the data structure at all.
Yeah, it's doing some amount of pattern matching, it's doing some amount of shortcutting. I guess what I've liked about this is that it allows us to very precisely kind of like diagnose reasoning breakdown.
Now, these are tasks that, would say a human 5-year-old be able to do these pretty easily? Like, here's a sorted list of numbers, insert the number 7 into the list.
I think so. Yeah,
Okay.
Yeah, some of them might be a little more difficult than what a 5-year-old could do. So, for example, you could imagine building what we learn in an intro algorithms or intro data structures class would be like a binary search tree, a balanced binary search tree to maintain like a sorted list of integers or something like that. And then in say graphics, you start to work not with 1D data, but 2D data, 3D data, and then we have beyond binary trees, we have like 2D trees, 3D trees, KD trees. And so these might be more difficult than what, say, a 5-year-old could do. But so definitely like an 8-year-old or something, if you taught them the definition of, say, like a 2D tree, the generalization of a binary tree, they ought to be able to do it. But what we find is that the LLMs, when you give them data that's not uniformly distributed in a 2D plane, but is somehow like concentric circles or moon shapes or things like that, somehow it's not able to build these 2D trees very well.
Yeah, well, that's definitely very disturbing. I see. Well, it's great that you are developing these benchmarks that can be used to test the reasoning skills of these machines in sort of a sensible way, where the instances actually test the underlying concepts rather than just pattern matching or just coming from some very easy distribution.
Yeah, exactly.
So assuming that these benchmarks are put out there and that perhaps companies are able to train models to be able to solve these sort of questions, suppose they are able to actually get them to do what these basic data structures do, maybe that would make it easier for them in the future to actually learn better algorithms?
Yeah. We view it as kind of like a first step, or like a very diagnostic kind of step towards understanding like more general reasoning capabilities of models. Because when we ask a model to do some kind of like complex reasoning task for us, it does have to do a lot of these kind of like learn from primitives, and then compose like primitive reasoning skills into longer, more complex chains of reasoning. And so yeah, we view this as kind of like a diagnostic way of understanding, like, okay, what are the different types of primitives when it comes to like reasoning, and in particular algorithmic reasoning, and yeah, where do these break down? So yeah, one could hope that if the models get better at this type of compositional reasoning, that they'd be better able to help us do like complex tasks, like planning and routing and things like that.
Well, it sounds like a really beautiful and impactful line of work.
Thank you.
You know, yeah, congratulations on doing this stuff. So, you know, actually, I thought that maybe we could, find out a little bit about your background. Like for example, at what stage did you kind of decide that you wanted to be an academic in this sort of mathematically very sophisticated field? Sort of when did you sort of decide to get into this racket?
Sure. Yeah. So my dad is retired, but he was a professor of music history, actually, at Middlebury College in Vermont. I thought that I was going to be professional violinist till I was 17, and then I decided I wanted to do academics instead. And really, it was like I feel like my dad had been telling me my whole life that being a professor is the best job in the world to have. And so
It
I
is.
think,
It really is.
yeah,
Yes.
once I decided I wanted to do academics, I kind of felt I had no choice but to become a professor in whatever field I decided to go into. And then, so when I was in maybe like sophomore year, my mom was a high school math teacher, so I always loved math, and so I continued taking math in college. I was kind of like afraid to do proof-based math before I finally started doing proof-based math, and then I discovered I loved writing proofs. And then finally, like in my sophomore year, I started taking computer science classes and loved computer science, continued to love math. I majored in math and minored in computer science. But what really made me decide to go into like more theoretical computer science was I studied abroad in Budapest in my junior year, and the Hungarian math tradition, as you know, is like extremely strong in combinatorial optimization and combinatorics and like this theoretical computer science. And so that's what made me decide to do more like theoretical computer science in my PhD.
I see. Okay, so it sounds like your work actually is across several communities. There's theoretical computer science, there is machine learning, there's maybe operations research, and so on. So have you found them sort of very welcoming as a whole, or is there one that you really like the best? Or?
Yeah. Yeah, so right. I really went into PhD thinking I would just do theoretical computer science, and that was it. But I got into like more theoretical machine learning in my PhD, and also, so that was my one PhD advisor, Nina Balkan, who's very central in the theoretical machine learning community. And then my other PhD advisor, Tuomas Sandholm, is like kind of the direction that we ended up pursuing was much more oriented towards like integer programming and operations research. And and I, in particular, started to think about kind of more beyond worst case analysis applied to integer programming and math optimization. So that's how I got into operations research as well. And yeah, I think, let's see, of the like most welcoming communities, I would say that I've been a part of, actually, let's say quarter of my research has been in the more economics and computer science community, and that community I've found to be like incredibly welcoming and incredibly warm community. I love the community in part because all my friends are in that community. And I continue wanting, even though my research I feel like has slowly drifted away from Econ CS, I still want to publish in that community just because I love going DEC and spending time with my friends in that community so much. So I think that really speaks to the value of having like a warm and welcoming community, and that encouraging people to want to be a part of and contribute to that community.
I see. And so is the community a little bit smaller than CS theory? Or?
Yeah, maybe perhaps a little bit smaller. Yeah, towards that end, like actually, and you've helped us with this. Some friends of mine and I have been working on developing similar kind of like mentorship and community building activities for the theoretical machine learning community as well. So yeah, trying to do like mentorship events, how-to talks, all these sorts of things to try to get people, like young students, to feel welcome and included also in like other communities too.
Yeah, absolutely. Okay. Well, obviously times are, changing very rapidly. So in terms of where academia is now positioned, do you feel that it's a great time to be an academic, or is this a time where where a lot of stuff is actually happening in industry, and maybe that's the place to be? It's hard to tell. I wouldn't dream of leaving this, because there's so much that's good about about the setting. But how do you feel about this?
Yeah. I mean, definitely, it's an incredible time to be in industry. But for me in particular, I think I've always felt just incredibly lucky since like the first day of my PhD to be able to spend all day, every day, thinking about things that I think are super interesting. So I always say that like my favorite state of being is the state of being like intrigued.
Yeah,
That's my
right,
favorite
right.
state of being, and for me personally, and my own personality type, I think that being in academia gives me the opportunity to just be very curiosity driven and try to like pursue that state of always being intrigued. And I have never done anything other than being in academia, really. So it could be kind of like a bias, but I personally feel like academia is the best place for me.
Right, right. No, I feel exactly the same way. Just the ability to think about stuff all day long. And, sometimes it doesn't even look like work to other people. Like I'll be lying on the couch at home thinking about stuff, and my family doesn't believe that I'm actually working. They think I'm taking a nap or something like
Sure.
that. They just don't understand,
Yeah.
But yeah. Okay, Ellen. Well, thank you very much for sharing your perspective and your experiences. It has been an absolute delight chatting with you.
Thank you. Yeah, thank you so much. It's been a pleasure.
Yeah.